Hello. In this video, I'm going to explain problem 16 from the 2014 F equals MA contest. In this problem, we have an object of mass 1 moving at a speed v0, and that collides with an object of mass 2, and we're told that the object of mass 2, or that m2 is equal to alpha m1, and alpha is less than 1. So notice that m2 is less than m1. And then, however, alpha is ultimately a fixed quantity for this problem. And then we're told that the collision could be completely elastic, completely inelastic, or partially inelastic. And so we have a spectrum of possible collisions. And then we're told that afterward the objects move at some speeds v1 and v2. And we're told that, the collision is one-dimensional and the object 1 cannot pass through the object 2, standard collision sort of restrictions for a simple collision problem. And then we are asked to find sort of bounds for the speed of object 1 in terms of its initial speed. So, how can we do this problem? Well, what do we know? So how are we going to find these kinds of bounds, and how do we know when the extreme case occurs? Well, here's what we do know. If you look at the center of mass frame of reference, then what you're going to see is you're going to see m1 and m2 moving in toward each other, and then afterward, you're going to see them heading outward. That's m1 and m2. And the critical thing is this, that m1 must be moving left after the collision. And the reason is that because m1 cannot pass through m2. And so because of that, ultimately m1 must always stay on the left of m2. That can never change. And thus, when they collide in the center of mass frame of reference, it must be m1 that goes left and m2 that goes right. Otherwise, m1 would have to pass through m2, and that cannot happen. And thus, we know that the speed of m1 must always be less than or equal to the center of mass speed. Really, equality, so we know that v1 is less than or equal to the center of mass speed, and really, equality would occur if literally m2 had no mass at all, meaning that m1 was basically not colliding with anything. And we would see that basically what we get is that, or excuse me, equality occurs when the collision is inelastic, I should say perfectly inelastic, just to be clear, meaning that the two objects would move together, because you would have m1 and m2 both moving together at the speed v center of mass, so the center of, So, what is the center of mass speed? Well, it's equal to the total momentum, so that's m1 v0, divided by m1 plus m2, which is the total mass. m2 is alpha m1, and so we would get v0 times 1 over 1 plus alpha. And remember that v1 is less than or equal to this, and thus v1 over v0, which is equal to r, we'll get, or r1 I should say, then r1, which is v1 over v0, is less than or equal to 1 over 1 plus alpha. So let's box that. Now when does the minimum occur? Well, in the center of mass frame of reference again, the min occurs, because the center of mass has a fixed speed, and so the minimum velocity of object 1, or they ask for the minimum speed, but ultimately I'll show that that matches with minimum velocity. It occurs if m1 or m1 and m2 move away from the center of mass as fast as possible. Thus, m1 will have the largest possible negative velocity relative to the center of mass, and thus it will have the largest possible negative, or the lowest possible velocity. And this occurs when kinetic energy is maximized. Now, we're told that this collision is elastic, partially elastic, or perfectly inelastic. It is not, importantly, super elastic, meaning that kinetic energy increases. A super elastic collision would be, for example, a particle exploding into two pieces, meaning that the total kinetic energy would actually increase. But in this case, the maximum, there is no such option, and so it will be maximized when the collision is elastic. And so now how will we compute what happens in this case? Well, afterward, we have two critical equations, which is that m1v1 plus m2v2, or I'll just start writing alpha m1 v2 equal, that's the total momentum after the collision, equals the total momentum before the collision, which is m1 v naught. And then we also know that this is an important theorem for elastic collisions, which I'm not going to prove here. That deserves a video of its own. But basically that the velocity at which the blocks approach each other before the collision equals the velocity at which the blocks recede away from each other after the collision. So what is the speed at which the blocks approach each other? It's v naught, that's before the collision. And basically it'll be the difference in the two velocities. And so basically another way of saying it is that the relative velocity of one block relative to the other changes sign. And so m1 is moving toward toward m2 at a speed v naught, and so afterward m2 will be moving away from m1 at a speed v naught, and so we'll see v2 minus v1 is just v naught. And now we can solve for these equations for v1 and v2. So let us do that. So we know that v2 is equal to v naught plus v1, and we can plug that into the first equation, m1 v1 plus alpha m1 v1 plus alpha m1 v naught equals m1 v naught, and thus we can solve and we can cancel all these m1s, so we get v1 equals 1 minus alpha over 1 plus alpha. Notice, or times v naught. Notice that this is always greater than 0, because we're told that alpha is less than 1. And thus, and remember, this is the minimum possible velocity, and yet it's still greater than 0. And thus we can see that minimum speed will be at minimum velocity. Because otherwise, if alpha were greater than or equal to 1, what you would find is that the minimum speed would of course just be 0, because you could find some possibility where the speed would be 0 for either a perfectly elastic collision if alpha was equal to 1, or if alpha were greater than 1, you could find a partially elastic collision where v1 would become 0. So, or partially inelastic. So minimum speed is minimum velocity, and thus we see that r1, which is v1 over v naught, is greater than or equal to 1 minus alpha over 1 plus alpha. And thus we have these are two bounds, and clearly anything between those two bounds is possible if we have a different share of sort of how inelastic the collision is. And so R1 lies between 1 minus alpha over 1 plus alpha and 1 over 1 plus alpha. And thus we get that option B is our answer. Something interesting is that even our first condition, when we determined that R1 was less than or equal to 1 over 1 plus alpha, that was actually the only option with this as the upper bound. And thus, from there, you might already be able to conclude that this was the correct answer, even without doing the elastic collision stuff. Anyway, that concludes this problem, and I hope that was helpful. Thank you for watching.